is an ideal FET. So the two contacts of the switch is open. So let me just do it directly. Although the notes, I'll type the results also in the notes. Wow, it's taking a long time to change your screens. It's taking a very long time to change your screens. I'm using a very high speed internet here. Okay, let's see. If it is too slow, then I'll go back to my notes. The type notes rather. So VMT is with respect to the ground. And then you got your R7 and R8. So this is switch S. So here switch S is equal to open and V0. So let's call this one V01 of T when switch S is open. I think this was R, and this I think was R7 and R8, or vice versa. I can't remember. I can go back to it. So let's consider case 1 when the switch is open. In my notes, I don't know if I've started with the switch closed. No, I think in my notes I've started with the switch closed. Let me follow my notes. So for the switch is closed means the control voltage to the FET is equal to 0. So when the switch is closed, we can draw an equivalent circuit. We can draw an equivalent circuit of this. So the equivalent circuit you'll have your input and go to R7 to the ground. The feedback resistance, sorry, the input resistance, the feedback resistance. So this is your R7, this is your R8, And this is your output voltage, which we are calling V01. And the VMT is our input with respect to the ground. So if you look at this circuit, so long as the internal resistance of our source VMT is less than R7, and here I'll assume VMT is an ideal voltage source, then R7 does not affect it. So this equivalent circuit is just our normal inverting amplifier. So this is equivalent to the normal inverting. Okay, it's just a normal inverting amplifier. Therefore, we can just say that V01 would just be in general minus R feedback over R input into Vm of t but what is our feedback resistance? Its value is R. What's the input resistance? Its value is R into Vm of t, and therefore this is just minus Vm of t. So we can say that thus when S is equal to closed, output is equal to Vm of t times -1. So that's the first result that we obtained. So when the switch is closed, or when the input to the gate of our FET is 0, or approximately equal to 0, then the switch is closed, and the output is the input times -1. Now let's consider case 2, when the FET is off. So let's consider case 2. When S is open, i.e. FET is off. So for this case, our equivalent circuit will be so this is your Vm of t at the input. Then you got your R7. And I'll consider this output to be V02 of t. So that is our R7, then R8. Now, who can help me solve this one? Who can help me solve this one? Remember, the switch is supposed to be between here and here, but it is open. It is open. Okay. So for us to solve this one, we know that the op-amp is a linear device, is being operated in its linear region. So we can simplify the input of this circuit to have two sources. So we can write that this circuit is equivalent to having for all this Vm of t's with respect to the ground. So since the op-amp is being operated in linear region, we can use the principle of superposition, where V02, which is the output of the op-amp, is the summation of the response due to source connected to the inverting input only when the other source is grounded, plus the source connected to the non-inverting input and the first source grounded. Hope everybody has understood that. This is because you're operating the op-amp in its linear region. So let's consider the output due to the non-inverting input only. So we can say that V02 is equal to, I'll just call it V0 dash OT plus V0 double dash OT, where V0 dash of T is due to U minus only, and V0 double dash of T is due to U plus only. So let's get V naught of t. So let's get V naught of t. Sorry, V naught dash of t. So for this, we ground the other input. So the equivalent circuit will be Vm of t as your input, going to R, going to the feedback resistance, and R7, R8 are grounded. So this will simply be our non-inverting amplifier, which is minus Rf, Ri to Vm of t, which is equal to minus R, Rf is R, Ri is R, into Vm of t, which is just minus Vm of t. So that's the response due to the first source only, with the other source grounded. So next, let's get V naught double dash. Let's get V naught double dash. So next, V naught double dash of t, the equivalent circuit, we ground the first source, and then we feed VMT to R7 and R8, because VMT is with respect to the ground. So this is our non-inverting amplifier. So how do we get the output inside in this case for our non-inverting amplifier? So if we assume that our op-amp is ideal, means it's got a very high input resistance, then R7 and R8 will have negligible effect of VMT appearing at the positive input of the amplifier. So it means at the non-inverting terminal, the voltage will be Vm of t. And that voltage Vm of t, let's assume it pushes, because for the behavior of the op-amp, because of its high gain, the voltage at the positive input is identical to the voltage at the negative input. So if the voltage at the positive input was P, the voltage at the negative input will also be P. And that voltage P will send a current in this direction. And let's assume this current is I, and this current must pass through the feedback resistance. This side positive and the other side negative. So let's find out what I is. Or we can start with the simple equation that that V naught double dash of T will be equal to the voltage at the non-inverting input plus the voltage across the feedback resistance. So it will be equal to VMT plus I into R feedback. But R feedback is equal to R. So you can just write that Vm of T plus I into R, where I is the current that passes from the inverting input to the ground through resistance R. So we can say, but I is just equal to Vm of T divided by Ri. I stands for input, so it will just be equal to Vm of T divided by R. So if you call this equation, let's call this one equation 3, and let's call this one 4, and let's call this one 5. So let's just substitute value of I in 4. So we'll get that V naught dash, not double dash, sorry, will equal to Vm of T plus I is Vm of T divided by R into R. Call that 6. So this will be 2 Vm of T. So let's call this last equation to be 7C. And remember, the response due to the first signal only was this equation over here. Let's call it 2. So V naught dash was equal to equation 2. V naught double dash was equal to 2 Vm of T, which is equation 7. So let's call this first equation to be 1, which was V naught 2 of T. So if we sub of 2 and 7 in 1 was V naught 2 of T is equal to V naught dash of T plus V naught double dash of T. And this is our minus Vm of T plus 2 Vm of T which is equal to Vm of t. Let's call this equation 8. So we can draw some conclusions and say, remember V naught of 2 is when the switch is open. So we can say, thus, when a switch S is equal to open, output is Vm of t, or you can say is equal to input times positive 1. It's input times positive 1. So in conclusion, S closed implies input times minus 1. S open implies input times positive 1. Hence the name positive negative amplifier. So let's go back to my type notes. So I've just done the same implementation. This is just the circuit we're analyzing. This is your FET switch over here. So when switch is closed, output is input times minus 1. Switch open, output is equal to input times positive 1. Hence the name positive negative amplifier. Now each of these units or each of these blocks will be used as a modulator and demodulator. So we shall see it later on. Now in my notes, my modified notes, I've given you the characteristics, general characteristics of an N type of an N-channel FET. It looks like this. I don't know if you did it in your third year. In third year labs, we normally do semester 1 digital, semester 2 analog. I don't know when you people study FETs. But these are the characteristics of FETs. So this is drain current versus drain voltage for various grid voltages. So you see when the VGS is equal to 0, it's conducting maximum. As you start putting a negative voltage of VGS, the current becomes lowers. And of course, an FET has got a maximum voltage you can put across it before it breaks down. So in this region, it's breaking down. In this region here, between 0 and VP, this is called the pre-pinch-off region. This region, in fact, I'll show you some other characteristics. This region over here, where the voltage across the drain and source is linear related to the current, is called the ohmic region. It's resistive in nature. So this is called the pre-pinch-off region. And from VP and before breakdown, it's called the pinch-off region of the FET. And we don't want to operate the FET beyond this region over here. So this I just added extra. So this is the analysis I was doing. I've already done it. So if you want to do it, you can just follow my notes. I've done everything. These are the equivalent circuits we've been using. So This is what we did. This is all that we did. This was our last equation that one of the last equations that we did. As you can see here, I was saying that from equation 4, for this case over here, it is seen that when the switch is closed, the amplifier system multiplies. In fact, this typing error here, multiplies should be the input. Input by -1. And when the switch is open, the amplifier multiplies the input. By a +1. You can say hence, thus referred to as a positive gain, negative gain amplifier. Yeah, what's happening? What is happening? Okay, and hence, thus referred to as a positive gain, negative gain amplifier. Okay, we've done all that. It's all simple. Now, this space here I left for a graphical solution. So, this space I left for this. So, for example, supposing this is here. Supposing this is Vm of t, and then you got a slowly varying input voltage. So like that. And this is your clock. Or your control voltage. So this is your Vc of t. Okay. So let's assume that when it's high, the clock is high. So it means this voltage is approximately 0 volts over here. And this will be pinch-off voltage. What's required to turn the FET on? Let's assume it's -3 volts. V pinch-off. So it means here the FET, the switch, this implies S is on here. Here S is off. I'll just put for those two cases. And of course, it will repeat across. It will repeat across. So if we check the output of our positive gain, negative gain amplifier, let's assume its output will be given in this axis over here. So this axis is time. So this is the output voltage. V naught of the positive gain, negative gain amplifier. So we can consider intervals. Okay, so for the first interval, when S is on, what did we say? You multiply input by -1. So this first section over here of the curve, of our input curve, empty, you multiply it by -1. So you'll get a curve like this. And then the next interval, S is off, you multiply by +1. Next interval, S is on, -1. Okay, the intervals, let me mark them here so that you can all follow. So next interval is number 4. Switch is off. So we multiply by +1. So the input times +1, it will look something like that. So you can repeat. Next interval will be something like that. Multiply by. So S is on. It means times -1 of the input. Here it's times 1 times -1. Now I'll leave you to fill the rest. That's why I left that space over here. Okay, let's consider interval number 9. Interval number 9. The waveform is changing direction. I will assume it starts from the 0 of the top input waveform. So when S is on, you multiply by +1. So, sorry, you multiply it by -1. Because interval 9, we C of t. So here you're supposed to multiply times -1. But the input is going negative. So negative times negative, negative input times -1 will become positive. So it will look something like this. Then interval number 10, negative. So it will look like that. Interval number 11, -1 times negative will look something like that. So I've just done a few. So I left that space for you people to fill in, so you can fill in the rest. But the last interesting part, so this is how the modulation is done. The modulator multiplies the input with a negative or a positive in correspondence to the frequency of the switching signal. So actually what we've effected over here is actually pulse amplitude modulation. We effected pulse amplitude modulation. And we can recover this signal by passing it through another positive gain, negative gain amplifier. Now for that, I'll leave you that as assignment. That's why I left this space over here. So this will be called a graphical solution. So you can actually get this assignment over here, this one here, and I'll leave it for you. This is to show that actually we can recover the signals. So this first one here will be your modulator. And this is your demodulator. There's an error in the drawing. There's supposed to be an R7 and R8 should be identical. So here it's R8, R7. So you can, and also these clocks are in, these switches are in synchronism. The switches are normally controlled in synchronism. So this switch and this switch, and you have your VC of t. So when this one is going positive, the output is going positive. So then synchronism, so that you can show. So here, what is just missing in between over here, there's supposed to be an AC amplifier. It's supposed to be an AC amplifier, but if there's no AC amplifier, because this is just to show that we can recover whatever we modulate by using another identical circuit. So the modulator and the monitor are identical. So it's only the AC amp is which is missing over here. But this was just to show that we can recover the signal. We can recover the signal. So this AC amplifier, since there's a direct connection over here, it just means that the gain of that AC amplifier is unity. So this is another implementation of a positive gain, negative gain amplifier. Sorry, this is an implementation of a chopper stabilized amplifier using a positive gain, negative gain amplifier. Although this circuit we are seeing in front of us, this one just to illustrate that if, for example, this was your VM of T, I'll give you that as assignment, and maybe this is your clock frequency. Then the output, let's call it V0 triple dash output of a whole system will be identical. That I normally leave as assignment, just use it as a graphical solution. So this tells us that we can actually recover whatever was input by using this circuit. Now this circuit, as I've said, what is missing there is the AC amplifier. But this was just to illustrate that we can recover whatever we modulated with an identical circuit at the output. So with that, we come to the end of this section over here. We come to the end of this section and start the study of FET switches, chopper. So I think, I don't know if you studied the FETs in your third year class, in a theoretical class, but this on the left over here, I've got an experimental setup of how to get the drain source characteristics. Sorry, the drain versus, source voltage versus drain source voltage characteristics with respect to the gate voltages. So on the left is the experimental setup. On the right is some of the characteristic curves that you'll obtain if you are to perform this in the lab. So in this region whereby the drain current does not change with drain voltage is called the pinch-off region. And this region over here, this region here, this is called the pinch-off region or the ohmic region. And of course, as we increase the voltage across the drain and source, it tends to break down. Now you can see the curves after in the pinch-off region is very linear, much more linear than transistors, much more linear than the normal BJT transistors. But when you're using the FET as a chopper, the voltage across the switch will be very small. It will be about 50 millivolts. The voltage across our switch won't be these large voltages. For example, in that section graph, you can see it's showing from 4 volts to almost 24 volts. But most of our switches would be chopping voltages which are very small, below 50 millivolts. So we won't be operating in the region shown, most of the region shown by this graph, but we'll be operating in a region close to the origin. We'll be operating in a region close to the origin. I don't know if I got space over here. I'll just show you. So we'll be operating actually in this region over here. We'll be operating in this region, near the origin, where the voltage across the switch is about 50 millivolts, and the currents will be very, very less. So if you have to expand proper characteristics, is characteristics near the origin. So near the origin, you get curves just like that. So this is now a drain. It will be in milliamps, and VD source in millivolts. And this could be for, say, VGS is equal to 0. And this could be a curve for VGS is equal to, say, minus 3 volts. So you'll see maybe this middle one could be VGS is equal to, say, minus 1 volt or minus 2 volts. Because the voltage, because remember, our switches, we can see some configuration. Sometimes the switch is going to be in series. So if this is your signal voltage, okay, let me use VMT again. So this is our switch. So this is the switch in series with the load. We could be the input to the op pump. There'll be also be another configuration whereby we'll study where the switch is in shunt to the load. So the switch is our FET. And this is your input signal. Or most of the times, maybe I'll just be calling it VG. So the voltage across the switch is going to be very small. Because when you're setting choppers, we're considering amplifying very low level voltages, which can be considered to be almost DC. So the characteristic curve near the region is this figure, let's call it figure C. If this was figure A, this is figure B. So we're operating near the origin. So figure C shows us what is happening around the origin, because the voltage between drain and source will be about 50 millivolts. The currents will be very small, in order of milliamps to microamps. So we're operating in the ohmic region of the FET, or we're operating in the pre-pinch-off region of the FET. So when you're dealing with choppers, this is the region we're interested in. We're not interested in the large signal characteristics of the FET. So our switch is going to be operated in this region, where VDS is in millivolts, less than 50 millivolts. IDs will be very small, milliamps or hundreds of microamperes. So let's consider the notes I've given about the switch. So I've said here that the above is the characteristics of the FET. Suitable as a series or shunt chopper. So series means the switch is in series with the input signal and the load. Shunt means the switch is connected in shunt with the input and the load. So I've said, as the voltage and current levels to be chopped are small, remember we said in the beginning for choppers, they're typically less than 50 millivolts. The FET operates in a region well below the pinch-off region. Okay, I can add here, we can say IE, sorry, IE near the origin. Near the origin of the characteristics, and this implies the following. Number one, the channel behaves as a pure resistance, i.e., current and voltage are linearly related, whose values depend on the gate and source voltage. Gate depend on the gate, depends on gate to source voltage. Okay, that's correct. So this is just what it means. So we're operating in this region over here. If gate to source voltage is 0, we'll be operating in this curve. If gate to source voltage is minus 3 volts, we'll be operating in this bottom curve over here. That's what I mean. Now the important thing is here. If VDS is reversed, the chopper still behave as required, i.e., it can chop. It can chop both positive and negative signals, provided the gate channel junction does not become forward biased. And number 3, all lines pass through the origin, i.e., the FET, or meaning the FET does not suffer from offsets. So all that data is just from these characteristics next to the origin. So if VGS was 0, we'll be operating this curve. If we reverse the voltage across the drain and source, the current will flow in the opposite direction, unlike that the case for a BJT transistor. So it means that the FET switch can chop both positive and negative signals, while the BJT is not able to do that. So now let's consider errors caused when using the FET as a switch. So there are three possible configurations of switches, or three possible arrangements of the FET switch when used as a chopper. I drew for you two of them, but I can just draw them here again. So in my analysis, I've started with the shunt chopper. So in the shunt chopper, this one, it means if you got a generator, your signal normally have some protection resistance, then you have your switch. In shunt, we shall see them in detail when we start analyzing, and this is your load resistance, which is actually normally the input to the AC amplifier. So this is your switch, which is your FET. So that is called a shunt chopper. The next one will be called a series chopper. So with the series chopper, you shall see the circuit, but it's just VG. Now you put your switch in series with the load. So this is the switch. It's series with the load. VG generator voltage. Then the last one is called the series shunt switch. So you got a series switch and you got a shunt switch connected to your load. So there you have two switches. So want to see, you're going to want to study the errors generated by these switches so that we can decide on which is the best way to chop a signal. Is it putting the switch in series? Is it putting the switch in shunt? Or is it putting the switch in series and shunt? So to do that, we consider what is known as error analysis of the FET switch. Okay, so let's start with the first switch, which is the shunt switch. So we want to investigate how much error will be generated by this switch. So here's your generator. So this is your input signal that you want to chop. RG is the internal resistance of the switch, and R1 is normally a protection resistance, which is put in series. And here is your switch VC of T. I'm not completely drawing that circuit, but so VC, the control signal, will be put here between the ground So that will be VC of T. So that is your shunt configuration. So I've said that in this configuration, the switching device is in parallel with the load and is alternatively switched on and off by the gate drive. When the device is in the off state, the voltage is applied. Sorry, I'll read again. When the device is in the off state, the generator voltage is applied to the potential divider R1 in series with RDS off in parallel with RL. I'll just explain. Let me just read this first. When the device is in the off state, the generator voltage VG divides between R1, RDS on in parallel with RL. And I've said that R1 is included to protect the device when switching from a low impedance. Now let's start with the on state error. On state error is when the device is on, the switching device is on. So for this, we draw the equivalent circuit. So this is the equivalent circuit. So when an FET is on, the resistance between the drain and source is called RDS on. So in this circuit over here, this is your drain. And this point over here is your source. So the resistance between the drain and source is called RDS on. Since the device is going to be switched on and off, we normally use small letters RDS on to show that it's dynamic. Just like with HFEs or via transistors, we use small hf, small h, small f, small e to denote the current gain over BJT. And we use the capital HFE, capital H, capital F, capital E to denote static or DC gain over transistor. So this is the equivalent circuit. So let's find out the error generated when the device is on. So ideally, remember RDS is your switch. This point here represents your switch. So ideally, when the switch is closed or the FET is on, ideally the output voltage should be 0. But it should be a short circuit. But the FET is not an ideal device. It's got a finite RDS on. So that will generate an error in the output. So in the notes here, I've said that when the device is on, the output should ideally be 0, but because of the finite on resistance, typically 25 ohms, the output does not fall to 0. Thus, an error is generated at the output of our switch, and the error is given by error is equal to indicated minus true value or the ideal value. Now, indicated B will be our VL. True value is supposed to be 0. Now, let me just emphasize one point over here. And this is that for chopper FETs, manufacturers actually manufacture FETs for choppers. And for those specific choppers, the manufacturer will tell you what is RDS on and RDS off. And for a chopper, in which, for a chopper FET, in which RDS on is about 25 ohms, that's a very, very good chopper. That's a very, very good chopper. A very, very good chopper FET, rather. Let me just show you something here. Let's go to some data sheets here, which I got. For example, Funnel, this is an American company. So this is their chopper FET. They've got various chopper FETs. These numbers over here. So you can see the features. It says that this device is designed for low-level analog switching applications, sample and hold circuits, and chopper stabilized amplifier. So you cannot just go to Lithuli and get an FET and use it as a chopper. And let's look at some of the data sheet, some parameters given in the data sheet. So look at this, the small signal characteristics, RDS on, the drain source resistance. You can see this for this MMBF 4091 is 30 ohms. The next one, 4092 is 50 ohms. This is 80. This is a chopper FET. Let's look at one for Texas Instruments. So this one, they're just giving applications. So here in sample and hold, I thought I had the characteristics somewhere. Let me just see. No, they didn't give here. Was it on semi? Okay, let's forget it. But the important point I want to stress over here is that semiconductor manufacturers manufacture FET specific for chopper stabilized amplifier. You cannot just get any small signal FET and say you're going to use it as a chopper and expect it to work properly. Okay, so let's get the error generated by this switch. It's actually very simple. So error is indicated value minus the true or ideal values. So this is referred to as error on, because the device is switched on. So in this case, it will be VL, the voltage that appears across your switch when the device is on. So this voltage would be VL. I've written here, it would just be VL. minus 0, just VL. Okay, so but from this circuit, you can just see that you have a very simple circuit. You can just draw your VG, have your RG, have your R1, and then you got these two responses. And this is RDS on, and this is your RL. So you can combine these two and call these two to be, say, R equivalent L. So it just forms a potential divider. So VL, which is a volt, is the voltage at the output. So, excuse me. So VL just simply be VG, R equivalent L, all divided by RG plus R1 plus R equivalent L. That's just the basic that. Okay. And then we see what is R equivalent L, but R equivalent L is RDS on in parallel with the RL, or it's RDS on into RL, RDS on plus RL. Now RDS on is 25 ohms. RL is the input to your AC amplifier. So this will just be approximately equal to RDS on. Okay, remember RL is the input to your AC amplifier. Okay, that's the input to the next stage. Yeah. And this is normally quite high. Okay, RL is typically high. So you've got a high resistance in parallel with a very low resistance. This is 25 ohms. This could be hundreds of kilo ohms. It's approximately equal to that. So from this equation over here, let's call that equation 1, the VL will just be simply VG into RDS on over R1 plus RG plus RDS on. So that's the theory. I've done it. I've typed it over here, because when you type it takes a long time. The principle is the same. So the error is just R equivalent into VG, or divided by R1 plus RG plus R equivalent. That is this equation over here. And R equivalent is just RDS on into RL, RL plus RDS on. RDS on is 25 ohms, and RL is typically the input to the AC amplifier, which is very high. Therefore, RDS on is less than RL, so R equivalent is just approximately equal to RDS on. Therefore, the error from equation 3 over here, instead of R equivalent in equation 3, we can just write RDS on into VG, or divided by R1 plus RG plus RDS on. So that's the error generated by using the switch in shunt when the device is in the on state. So I've concluded that thus, for a given RDS on, that means a given FET or a given device, the error in the on state can be minimized by using large values of RG and R1. Means your generator resistance should be high and your protection resistance is high. Now, this requirement will be seen to contradict the requirement for minimum error of the off state, because the device is not only operating in the on state, it will be alternating between on and off, on and off. So next, let's consider the error of the same switch configuration in the off state. It calls the off state error. Now, because of editing, I pushed a lot of things, so this topic I think has moved somewhere. It's moved over here. Let's see. We can put it here. No, I can't put it because of the header. Okay, yeah, let's just leave it. So next, let's consider the off-state error. So the off-state error, the circuit is just the same. Still, the device is still in shunt over here. But now, the switch is off. So this is the equivalent circuit with the switch is off. So now instead of RDS on, we got RDS off. Now, when the device is in the off state, what we expect is that the output should equal to the input voltage. But due to the series resistance RG and R1, not all the voltage appears at the load, and this gives rise to an off-state error. So let's find out what this error is. So error is just simply indicated voltage minus the true value of the ideal voltage. And this error is called error of the off-state, or in simply, I'll call it error off. So error off is the voltage that appears at the output minus the ideal voltage. Now the voltage that appears at the output for this circuit, once again, you can combine RDS off and RL and call it R equivalent. So R equivalent will be equal to VG into R equivalent divided by the sum of the resistances, RG, R1 plus R equivalent. So I'll put it this way, minus VG for this part over here. Now to simplify this first equation, let's make VG common. So if I make VG common, this bracket is not in the right place. This one, there's an error in this bracket, but the second one is correct. This first bracket should read VG R equivalent R1 plus RG R equivalent minus 1. And then next you multiply inside and outside the bracket by minus 1. So you get minus VG into 1 minus R equivalent R1 plus RG plus R equivalent. So this one is okay. This second equation is okay. So now let's just simplify this second equation over here. I don't have time to edit this right now. Let's just move on. So let's make the denominator RG plus R1 plus RG to be common. So you'll get this other equation. You get this equation over here. If we call this first equation, let's call this one equation 2. Let's call this 3. Let's call this 4. Call this 5. So if you make RG plus R1 plus R equivalent to be a common denominator, then in the numerator, you're going to get 3. And then this from 3, this R equivalent will cancel this R equivalent. You'll just remain with the RG plus R1 in the numerator, all divided by RG plus R1 plus R equivalent. That's how we get. Wow, Even here, things have moved again. It should be like that. So this is how we get 4. And then we divide numerator and denominator. So the bracket of 4 by Rg plus R1. So you get 1, all divided by 1 plus R equivalent divided by Rg plus R1. But what is R equivalent? R equivalent is the parallel combination of this combination, the parallel RDS off into RL. So 2 resistors in parallel is R1, R2, all divided by R1 plus R2. And remember that RL is the input of our AC amplifier. RDS off, we get it from the parameters of the FET. And RDS off is typically 10 to the power 10 ohms, while the input of the op amp is a few mega ohms. So you got a very large resistance and paired with another resistance is small relatively. It works out that the combination will just be the smaller resistance. So that's the result we used over here. So R equivalent is RDS off into RL, RDS off into plus RL, but RDS off is 10 to the power 10 ohms, which is greater than RL. So we can say that R equivalent L is the same as RL, and therefore error off is minus VG 1 divided by 1 plus RL. Let's look at this, the equation. This was the equation over here. So this R equivalent, we just put equation 5 here. R equivalent is just RL divided by Rg plus R1, or R1 plus Rg. So this is how we get Rg plus R1. Have I typed 1 here, or this is an L? It should be R1. Okay, so we can make some conclusions over here. We can make some conclusions that from the above equation, we see that for a given Rg, remember Rg is the resistance of our source or of our transducer. So for minimum error, it must mean that R1 should approach 0, because if R1 approaches 0 over here, or R1 is small, then RL divided by Rg plus R1 will be large, and therefore the division of RL divided by this small number will be large. And RL should be large, because if RL is large, then the denominator becomes large, and therefore the error becomes small. Now this requirement contradicts the earlier requirement for the on state. So in practice, a compromise has got to be reached, and it's found that minimum error occurs when R1 is given by root RDS on into RL. Now this is just obtained by differential calculus. That's first year stuff. So error 1 plus error on plus error off should be minimum. So you can differentiate how error 1 plus error on varies with respect to either R1, because RD will be fixed, with respect to R1 and RL. So this is how we get the errors generated by a switch connected in shunt. or an FET switch connected in shunt, and how we design for minimum error if you have to connect the switch in shunt. Later on, we shall give some practical values so that you can physically see the errors generated by this configuration of a switch. Now, there are other types of errors also, which are referred to as non-quantifiable errors. These are errors which you cannot put an exact equation to because their values are dynamic and their values change. Their values are dynamic and their values change. So here I've drawn an equivalent circuit of the switch in shunt. So for example, this is the device. So this is your switching device. I normally draw if it is this way. This is your drain. This is your source. Now remember, this is your gate. So there's normally a capacitor from here to here. There's normally a capacitor, a junction capacitor or intellector capacitor there. So this capacitor here, we call it C, GS. This capacitor, we call it C, CDG. And of course, you got your control voltage. It's going to be varying, controlling the gate. So in this circuit over here, this is your drain. It's not a very good diagram. This is your source. And this is your gate. Not a very good diagram. These capacitors are very small for switching FETs, especially chopper FETs. Let's just go to some of the data. I thought I'd gotten one here. This one. Yeah. So for this on semi, this is given RDS on 30 and 60 under the capacitances. Here, input capacitance here, VDS is equal to 0. It's about 10 picofarads, and it changes. It's not a good data sheet. Let me check a last one. If I don't get it, we just move on. Let's see the one of Texas Instrument. Oh, funnel. Okay, for this funnel, you can see for this one, input capacitance is 16 picofarads, and the reverse capacitance is 5 picofarad. That's between the gate and the drain. So the input is done. So here we've gotten two capacitances, 16 and 5. Can't see the other capacitance is not given, but it's normally quite small. Okay, let's get out of here. So let me just draw a better diagram here. So we've seen one where this is 16 picofarads. And this was about 5 picofarads. And this one also is normally small, about 5 picofarads for chopper FETs. Okay, so I should visualize it that way. So typically the input capacitance is the capacitance between the gate and sources, and which is normally large. The other capacitances are typically 5 picofarads for chopper FETs. Now the problem comes when we use a rectangular voltage to switch the device on and off, on and off. So that's represented by a waveform going to the gate this way. So for example, if we start at this point over here, the input point over here, when it's going high, part of the signal can flow through this capacitor and appear at the output of our system. So you'll get a spike like that. And then when it is switching off at this point over here, you're going to get a spike like that, on, off. So these are the type of voltages which we call switching spike that appear at the output of our switch. And the average of the two peaks, the positive, they are not the peaks, but the average of the area below these two curves, the positive going curve and negative going curve, will give us an offset voltage, which it will appear at the output of this circuit over here, that output VL. So even when the input signal is zero, we can actually have switching spikes. And the average area of the positive plus the average area of the negative, if you add the two, it will give us an offset voltage. And that offset voltage will add to the signal which is being chopped and thereby give us an error, because that signal will be there, whether the input is zero or whether the input is short circuit or not. So these are called switching spikes. Okay, and these switching spikes are referred to as non-quantifiable errors because you can't put an exact equation to them. The reason being, as the voltage varies across the drain and source and gate and source, the values of the capacitance change. They're not static capacitances, they're dynamic capacitances. So actually the best way to get these switching spikes is to use an oscilloscope and connect it between the output, and then you'll be able to tell exactly what voltages we are actually getting. They're quite small because as you can see, those capacitances are very small. And therefore, if you're switching voltage, say like a kilohertz, the reactance of 5 PF will be very, very large. But we got to know that they can actually exist. So to reduce these switching spikes, to decrease these switching spikes, the following can be done. So I've written them down there. I've said that feed-through spikes are usually caused by inter-electric capacitances and can be minimized by the following. Number one, reducing the rate of change of the control voltage. Now in the diagram, I've shown switching with the rectangular pulses. Now rectangular pulses have got a very high rate of change when the signals are transitioning. So instead of using a rectangular waveform, you can use a ramp waveform. So a ramp waveform would be a waveform that goes something like that. It will still work. So the rate of change, remember in your digitals, you are studying time rise and time fall. So time rise is the time it takes for a waveform to change from 10% to 90%. Time fall, the time it takes from 90% to 10%. So you can slower the rate of change of the voltage. And if you slower the rate of change of the voltage, it means the switching spikes will be less. Because remember, this square waveform or this rectangular waveform, I said you can consider, if you take the Fourier transform, it can be considered as having lots of frequencies. So if we add all those frequencies in their correct phases, we get this rectangular waveform. So by using filters or by shaping the waveform, we can decrease the rate of rise of the waveform, the rate of fall of the control waveform, and therefore the switching spikes will be less because the harmonics of high frequencies will be less, and therefore this high frequencies, now the high frequencies are not there, and therefore the lower frequencies will get greater opposition to the reactance at 5 picofarads. The other thing, number two, is to decrease the load and the generator resistance. Decrease the load and generator resistance. Now, for you to be able to see that, you can imagine that you've resolved the square wave into its harmonic frequencies. So you can use linear circuit analysis to analyze the circuit. So if you look at this circuit over here, when the signal is going positive, the pulse, let's assume you use one frequency of this square wave, the most dominant. Remember, a square wave has got a fundamental which will contain the most energy. So you can use linear analysis. Just use the reactance of a capacitor. CDG is equal to 1 over X CDG. So this signal here, if we see, one of it will go in this path over here. Another one will go in this path over here. So the output, the signal at the output, let me make life easy. So if you look at this circuit, this is your control voltage. It's going to your gate. And then it goes to the drain through this. And then you got your RDS. So this is your drain, this is your source. Let's assume this is your VC of t, so you can get the Fourier transform to get VC omega. Now, if you look at the output circuit, we can put it over here. This is your RL. And then from D to the input circuit, if you look at point D, going back to the input circuit that way, I can start at D, and then I'll get R1, and then I'll get RG, and then you have VG. If you assume it's at the ideal source, like that. So if analyzing the circuit, we can consider even VG is equal to 0, so it gets short-circuited. And of course, the voltage between here and here will be a VL due to this VC of t. So if you just consider one harmonic, which is the fundamental, this reactance of this capacitor, you can just represent it as a reactance. We'll call it XGD, which is 1 over 2 pi F C GD, where F is the fundamental of your control signal. So the voltage that appears at the output due to the switching only for this one fundamental frequency, we have to get, so V naught due to switching spikes will be equal to the parallel combination of all this. So you'll get RDS in parallel with the RL, in parallel with R1 plus RG, all divided by XDG plus the parallel combination. Now I don't have space, so I'll just call it RL, R equivalent L, which is the combination of RDS, RL, R1 plus that. Now if you look at that equation over there, of course all this times VC of t, the amplitude of VC of t. The numerator will be times the amplitude of VC of t. I do have a space to put it over here. Let me remove this a bit. V times the amplitude of VC of t. Here, this is just the amplitude. So if you look at this equation over here, if RL is 0, the whole of the numerator is 0. Of course, RL is not 0. So if you look at this equation, remember RDS is dynamic. One time it will be maybe 10 to the power 10 ohms. The other time it will be maybe 25 ohms. So, and since RDS, which is dynamic, is in parallel with RL, so it means if RL is small, the whole function of the numerator is small, or if R1 is small, the whole function in the numerator is small. So if the numerator is small, multiplied by the amplitude of VC of t, everything will be small. So that gives us our second point there. That is reducing the load and generator resistance. Normally the generator resistance, you can't reduce it once your source is fixed. Once your source is fixed, if you got a device, a transducer, you can't change it. Okay, so the only thing you can change is your load resistance and your R1. And of course, a good choice of your FET. which will determine RDS. But remember, RDS changes from 10 to the power 10 to 25 ohms. So that is how we get this second point over here, reducing the load and generator resistance. So what we are doing, we're just using this equation here, which has been derived. We reduce any value or the parameters in the numerator. You decrease the amount of voltage being fed through the capacitance, XDG, XGD. And then the other one is to use a sinusoidal drive. So instead of using rectangular waveforms, you can use a sinusoidal drive. So the rate of change of a signal, which is sinusoidal driven, is less than, the maximum rate of change of a sinusoidal driven voltage is less than that of a pulse waveform. And hence I've concluded there that the effect of feed-through spikes is to give rise to a new offset error. A new offset error, and it may even overload the AC amplifier if its magnitude is large. So if you don't design your circuit properly, like if you use a very high frequency chopping, the reactance between the capacitance between the gate and the drain might be such that a very large voltage appears at the input to the AC amplifier, and that may overload it. Okay, so in general, the magnitude of the off and on spikes is similar, but the energy contained within the off spike is greater and produces a greater contribution to the offset voltage at the output. Now, for you people to do that, you just use this circuit over here. Just use this figure over here. Forget about all this. In the CRT, I used to ask this question over here, and no students could answer it. I don't know why. Most of the students have gone. Okay, so we'll do it in the next class. But just look at it this way. When the control voltage connected to the gate is rising, say, from a negative voltage to a positive, and it's rising from a negative voltage to a positive, then it means that RDS was initially off. So this was 10 to the power 10 ohms. And then we put a pulse. We use a positive pulse. Let me draw a diagram here. So this is the control voltage. So I'm talking about this interval over here. So let's consider the drain voltage. So during this interval, it means that the FET was initially off. So this sharp peak will rise, and then the FET turns on quickly for the air. Another curve will be small. So this area under here will be small. Now next, when the FET is on, and we put a negative going pulse at the input to switch it off, it means during this point, the resistance drain is changing from 25 ohms to 10 to the power 10 ohms. So it will give us a large time constant like that. So the time constant will be CDG into this resistance changing from 25 ohms to 10 to the power 10 ohms. So that's why I would say that the areas, now the curves are different because one has got a larger time constant. Okay, this tau over here, time constant, let's call it tau 1, will be RC, 25 ohms, into CDG, and this time constant over here, which if you call tau 2, will be equal to maybe 10 to the power 10 ohms R into CDG. So that's what's responsible for the area under the curve. So I think I'll stop over there. Because I think you got another class. So we'll leave questions to next time. So thank you.